You ever hit the power button on your computer and just wait? It feels like a bit of magic, right? But what's really happening is one of the most perfectly choreographed relay races in all of technology. So let's dive in and demystify that incredible journey from a silent black screen all the way to your fully loaded desktop.
I mean, it's a question we've all kind of wondered about, right? You press that button, maybe go grab your coffee, and by the time you're back, everything is just there. But that little gap, that short wait, is absolutely packed with a lightning fast series of handoffs, checks, and initializations. We're going to break down that 15-second miracle step by step. All right, so it all begins right here. This is the very first leg of our relay race. It's that initial spark that kicks everything off, where the physical hardware wakes up and gets its first crucial set of instructions.
So, the second you hit that power button, bam, a jolt of electricity zaps the CPU, the brain of your computer. And it wakes up in this really basic state with just one single-minded mission hardwired right into it. Find the system's firmware. That's it. Its whole job is to find this little piece of code on a special chip and get to work.
Okay, so the firmware's first job is kind of like a runner's warm-up lap. It does this thing called a power-on self-test, or POST for short. It's just a super fast check to make sure the absolute essentials, we're talking RAM, CPU, are actually there and working. If you've ever turned on a computer and just heard a series of angry beeps, yeah, that's the POST telling you something is seriously wrong. But if it's happy, it starts scanning all your drives in a specific order, looking for the next runner in our relay.
And this whole firmware thing has evolved a ton. For decades, computers used this classic, old-school text-based thing called BIOS. But today, pretty much every modern computer uses UEFI. And it's a massive upgrade. We're talking faster, way more secure, and it's what gives us those nice graphical interfaces with mouse support before the OS even loads. Honestly, this shift is one of the biggest reasons your computer boots up so much faster now than it did, say, 10 years ago. Okay, so the firmware has done its part. It's checked the hardware, it's found the next runner on the storage drive, and now it's ready to pass the baton. This brings us to the second super important stage of our relay, the bootloader. And this handoff is really the first link in what's called a chain of trust, where each piece of the puzzle totally relies on the one before it to have done its job perfectly. So what is a bootloader? Well, think of it like a specialist. It's this tiny, laser-focused program that has one job and one job only. Find the heart of the operating system, the kernel, and load it into the computer's memory, or RAM. That's it. It's the critical bridge between that initial hardware check and the massive, complex beast that is your operating system. And yeah, every major OS has its own. If you're a Linux person, you've probably seen Grub. Windows, well, it has the Windows Boot Manager, and macOS uses a thing called boot.efi. They all do the same basic job, they're just built for their own specific operating system. And look, this isn't just some abstract technical thing. If you've ever set up a dual boot computer, with both Windows and Linux on it, that menu you see, the one that lets you pick which one to start, that's the bootloader. That's Grub, right there, doing its thing. It's literally pausing the relay race for a split second to ask you, hey, which runner are we handing the baton to?
All right, here we go. We're at the most important part of the race, the anchor leg. The bootloader has found our star runner, the operating system kernel. It's loaded it into memory, and now it's handing over complete control. This is the big one.
So what is the kernel? I mean, at its most basic level, the kernel is the operating system. It's the central core, the master controller, the conductor of the whole orchestra. It has complete control over everything, the CPU, memory, storage, all of it. It's the ultimate bridge that lets your apps, like a web browser, actually talk to the physical hardware, like your network card. But this brings up a funny little paradox, right? A real chicken and egg problem. The kernel needs drivers to access your main storage drive, but all the drivers are stored on that drive. So how does it even get started? Well, the solution is this temporary little file system called an initramfs that gets loaded into memory with the kernel. You can think of it like a tiny little toolkit with just the one special key needed to unlock the giant toolbox on your main drive. And once the kernel has control, it just explodes into action. I mean, it starts initializing all the complex hardware, your graphics card, your USB ports, everything. It sets up all the sophisticated memory management that lets you run a bunch of programs at once.
It officially mounts the main file system, which just means it makes your C drive and all your files accessible. And then for its final trick, it kicks off one single master process that's going to build the rest of the world that you actually see and use. Okay, the kernel has taken complete control of the machine, and now we are in the final sprint to the finish line. It's time to hand off that last baton to what we call user space. And really, that's just a fancy term for everything that isn't the kernel. This is where the desktop you know and love actually gets built. So that very first process the kernel starts, it's usually called init, or on most modern systems, systemd. And the best way to think of it is like a general contractor for a construction project. It has the master blueprint, and its job is to start bringing in all the subcontractors in the right order, getting the networking online, firing up the sound service, handling user accounts, the whole shebang. And this is that final rapid-fire sequence. The kernel hands off to init, init starts firing up all those background services, and one of those key services is the login manager, the thing that's responsible for drawing that username and password screen. The second you see that login screen pop up, the relay race is over. The computer is up and ready for you. So when you boil it all down, that's what's happening. The entire boot process is this beautiful, perfectly timed chain of trust. It starts with a simple hardware instruction, which hands off to the firmware, which passes the baton to the bootloader, which then hands control to the massively complex OS kernel, which finally builds the entire environment you use every single day. It's an incredible sequence. And this is an incredibly robust process. It happens billions of times a day, all over the world, without a hitch. But it really makes you think, doesn't it? Every single one of those steps has to work perfectly for the next one to even begin. So what happens when just one single link in that intricate chain of trust breaks?